Welcome everybody. This class is gonna be focused on the basic principles behind network security. We will start with some simple examples and we will find more complicated attack. But let's start with the basics. So the Internet Protocol Suite is a set of protocols that actually makes the internet work. The basic idea is that these different protocols are layered, so there are lower level protocols that provide service to higher level protocols, which in turn provide services to even higher level protocols, and they all work together with the goal of providing communication services to users across the internet. And you can see in this view that there is a physical layer. This is how information is actually transferred, and there are link layer protocols that fundamentally allow directly connected devices to exchange messages. On top of link level protocol, you have internet level protocols such as the IP protocol, but also other protocols like ICMP and IGMP. And then we have the transport level protocols such as TCP and UDP. At the highest level, we have a plethora of application protocols. You are familiar, of course, with HTTP or DNS, but there are countless protocols that use TCP and UDP as transport for their data. Let's start with the concept of IP addresses. IP addresses are 32-bit values that we usually represent as 4 octets separated by periods, like in this case, 128, 111, 48, 69. The concept behind an IP address is an endpoint of communication in an IP network. So you can think about it like the address of a house. What the IP network does is moving packets from one IP address to another. Initially, the way in which the IP address space was structured was defined by a number of classes. So every IP address would have a specific class. For example, that would be a class A IP address, which had a network ID part that is composed of 7 bits and a host ID part that is composed of 24 bits. The net ID specifies the network. We can look at it like the building. And the host ID is the actual endpoint, which would be, for example, a specific apartment within the building. And you can see here with 7-bit, you can represent 128 networks that were actually pretty big. And each of these networks could contain up to 16 million hosts. Similarly, you have a class B that is identified by a prefix of 10. They would have a net ID of 14 bits and a host ID of 16 bits. So you can get more network, 16,000 networks, each of which has 65,535 hosts in each. Or you can have the more common class C, which it is identified by a prefix of 110, which would have around 2 million networks, each of which has a host ID of 8 bits for a maximum of 256 hosts. And then you have other prefixes that define multicast and other special addresses. So you can see that the problem with this class-based IP address schema is that the moment you allocate to one of these big networks or one of these addresses, you have 16 million IP addresses that are allocated to that network. If that particular net ID uses only 2 of them, that means that the other 16 million that are not used cannot be used by any other network. And this is obviously a problem. And in fact, in February 2011, it was the last time that public IP addresses could be actually associated to new institutions. So we have officially ran out of IP addresses. One way to deal with this is classless interdomain routing, CIDR. And the basic idea here is to forget about the class-based IP addresses and instead use the concept of a flexible prefix where you can say, hey, I will consider, instead of only consider 7-bit, I can consider, for example, the net ID to be at bit 27. And by moving flexibly the net ID, host ID sort of differentiator, the threshold, you can have a lot of different sizes of networks as you need. And you can break down the original very big networks in smaller networks to make the IP allocation more flexible so that you don't have to waste all those IP addresses. And of course, in order to do that, you need to specify two important concepts, which are the IP address, but also the net mask, as we will see. There are some special addresses that we have to know about. One is the network loopback interface. Those are addresses that start with 127, typically 127.0.0.1. This is an interface that fundamentally allow communication within the host. And so even if your host is completely disconnected from any network, no wireless, no wired network, you can still have processes communicate with each other using the loopback interface and internal network. You can actually have special values for the host ID. For example, if you have net ID equals 0 and host ID equals 0, you can say that you want to specify this host on this net, or you can have a host ID that specify a specific host and you leave the net ID equal to 0. These are all ways to specify a specific host in specific cases, such as the booting procedures. Also, if your all bits are set to 1, you consider that to be a local broadcast. And if you have a net ID plus a host ID with all bits set to 1, you can do a net directed broadcast. And actually that means that the packet, as we will see, will be routed to reach this particular network as specified. And once it has reached the network, the packet will be broadcasted to that destination network. Then there are a number of reserved addresses. For example, the 10 addresses, the 172.16 and then 192.168, which are ranges that are devoted to internal networks, and they're considered non-routable. That means that if one of those addresses will appear on the network, the result will be that the packet will be dropped because they're not supposed to be externally visible. But let's talk about the IP protocol, which is sort of the glue of the internet. The IP protocol provides a service that is connectionless, unreliable, best effort delivery service, datagram delivery service. This means that what IP does, it guarantees that one datagram can go from one IP address to another. However, many things can happen during this delivery. The packet could be dropped, so the delivery actually never happens. It could be even that the packet gets duplicated, so you get 2 copies of it. It could be that the packet, gets, for example, modified and broken down during the delivery. It is also the case that if you send packet A followed by packet B to the same destination, it is possible that the destination will receive packet B and then packet A, so no ordering is guaranteed. And of course, we'll see what it means between sending datagrams between 2 nodes, as we will see very soon for direct communication. So when 2 hosts are directly connected, IP relies on a lower level, a link level protocol, such as Ethernet, FDDI, and so forth. If you look at the IP datagram, there are many fields that are very important. Of course, there is a header, an option in the header, an option section, and some data. There is a version. The current version is 4, and at the same time, we will see also there is currently the deployment of version 6. There is header length that tells you how many bytes the header is, actually multiples of 4. So the smallest possible header is 20 bytes, so this value would be 5. If you have more than 5, then you will have, you can use this information to understand that there are options in the header. There is the total length of the datagram, and you can see that since the total length is 16 bits, the biggest possible IP datagram that you can send is 65,536 bytes. We have an identifier, and we have some flags and a fragment of set that, as we will see, are used in fragmentation. And then we have a time to leave, the protocol, and the source and destination IP addresses. So those are all important information that allow to understand, for example, what is the protocol to be used to interpret the data inside. And these are just, description of what I said. The IP option that I mentioned are variable in length, can be used for different things. For example, they could use for recording the route, so that part is updated with the various gateway that are traversed in the delivery process, could be used to record timestamps and other functionality. Of course, in the delivery of IP datagram, as I said, for direct communication, the IP datagram header and data becomes the payload, so the data of a lower level frame, such an Ethernet packet. So let's see how it happens that a datagram is delivered between two directly connected hosts. So here you can see that there is a first host, and I'm using here as an example 2 hosts connected by an Ethernet network. In Ethernet, as we will see, the addresses are described by this series of 6 bytes. So there are 48-bit addresses. And this host has an IP address of 111.10.20.121, and this Ethernet address. And this host has 111.10.20.14 as an IP address and has this Ethernet address. So in order to send the datagram from one place to another, the sender, in this case this host, create an IP datagram, and that here is represented in red, that goes from the IP address to the destination address, and encapsulates this datagram into an Ethernet frame that goes from the Ethernet address of the sender to the Ethernet address of the receiver. This datagram is then put on the network, and it's automatically delivered to the destination. Now, this is all very simple. Let's see what Ethernet is, because it's so widely used nowadays that it's important to understand its implication and how it works. We have seen that the addresses are 48 bits. It uses CSMA CD, so carrier sense multiple access with collision detection. The basic idea is that machines that are on the same network, when they have to send an Ethernet frame, they start communication and they verify that what they're sent on the wire is actually correct. It's actually has not been sort of tampered with or modified through a collision with somebody else speaking at the same time. And once this is verified, or if the integrity has been compromised because 2 devices spoke at the same time, they have a way to back off and retry later, making sure that there is no conflict between the two. The type of frame has 2 bytes, as we will see, can be an IP datagram, but can also contain messages for ARP and RARP. And then we have the data. The data has a maximum called an MTU, maximum transfer unit, of 1500 bytes. As you can see, obviously, IP diagrams can be a lot bigger than 1500 because they can be as big as 65,000 and some. And therefore, they have to, the sender, most of the time, will create smaller IP diagram to fit them into this smaller frame. Or we'll have to use, as we will see, fragmentation. This is an example of an Ethernet frame, destination, source, type, some data, and some checksum there. If the type is 800, it will be an IP datagram. 806 is ARP, and so forth. As you can see, ARP seems to be important. It's important because if you look at what happened in direct delivery, we assumed that both ends knew the Ethernet address and the IP address of the partners of the communication. But this is not always the case. You might want to talk to an IP address about which you don't know anything, and so you want to find out what is the hardware address, for example, the Ethernet address, associated with that IP that you want to talk to on a directly connected network. So this is what happens in ARP. When host A wants to know the hardware address associated with the IP address of host B, with whom host A wants to communicate by sending an IP datagram, host A broadcasts a message and asks to anybody, hey, I want to talk to this IP address. Who has the information about the associated hardware address? And of course, host B is on the same network, sees this message, and realizes, hey, this guy is talking to me, wants to talk to me. So we'll send back a message, say, I am host B, the IP address that you want to talk to. By the way, this is my hardware address. Host A, when it asks the question, also includes its own hardware address. So with just one exchange, at this point, both endpoints know both the IP address and the hardware address of each other. And therefore, communication can happen. So this is how an ARP message looks like. You can see there is, the hardware type, the prototype, the size. These identify, the mapping sizes between the higher level protocol and the frame level protocol, the operation, the sender Ethernet address, the sender IP address, the target Ethernet address, and the target IP address. This one message can contain all the information together. Of course, the up field specify if this is a request or a reply, and then this is the data that will be transferred. Here we have an example of a transfer, and you can see that there is a command up there that say ARP-A. This is a way to show what is currently cached in the host operating system in terms of mappings between Ethernet address and IP address. And that command returns nothing at the moment. This host doesn't have any mappings cached. But then host A, which happens to have IP address 192.168.1.100, tries to ping host B. And you would imagine ping is, as we will see later, the exchange of two messages, an ICMP request and an ICMP reply. These are two IP packet, actually ICMP packets. But before anything can happen, you can see here two packets. The first is from this Ethernet address to FF, which means local broadcast. So this is a way to broadcast to everybody on the same Ethernet link a message. And this is from this guy say, hey, who has the address of 110, the guy we want to talk to, please tell to 1100, which is the requester. And at this point, thank you to this first ARP request, this guy sees the broadcast and say, oh, these guys want to talk to 110. I am 110. I have to tell him what my Ethernet address is. And at this point, the ARP reply will go back, and you can see it here. It's from the Ethernet address of that host, host B, to the Ethernet address of this. So it's not a broadcast anymore, because now they know each other, so it can directly reply something they say, hey, by the way, I am at this Ethernet address. At this point, it has been established that these two IP and Ethernet address are linked together, and now the actual packet can be sent, and the reply can be sent as well. And you can see how, since the ARP request already contains both the IP address of the sender, the ARP reply is the only thing that is needed to complete the information. And you can see on host A, now if you call ARP-A to see the cache, you can see that the values for host B have been cached, and on host B, the values for host A have been cached. So this is how you establish direct communication between directly connected hosts. Now let's look what we can do to attack this system. So in local area network attacks, our goal are the impersonation of a host, denial service, so to block a host from accessing the network, sniffing, so accessing information that normally we would not be able to access, or just, tampering with the way in which two hosts communicate. And all these attacks use some building blocks that we call sniffing, spoofing, and hijacking. And we will see them in detail. But first, we have to talk about hubs and switches. There is, in the very early day, fundamentally, in the super early day, you had something called vampire tap, where Ethernet hosts were actually connected by a physical cable, and each host would have sort of like a derivation going out of the wire, and fundamentally all hosts were sharing the same actual copper cable, and so it was a real shared medium. Of course, this has a lot of drawbacks. For example, if you break one of the cables, the whole network ceases to function, or at least it becomes partitioned. And so people move to hubs. Hubs are these little boxes, and every single host connects directly to the hub, and the hub itself implements a cable. This means that every host connected to a hub sees all the traffic of every host, even if it's not directed to them. So this is the example of a hub and switch. So here you have a box. They look identical. But a hub has ports, and a switch also has ports. But if I put a number of laptops right here, if these two laptops talk to each other like this information will also be sent to this laptop, even though this laptop has absolutely nothing to do with it. This is because it's a simplification, but it also has the drawback that the overall amount of traffic that can be exchanged is actually limited by the aggregate of all the bandwidth. And this is called a hub. In a switch, instead, this is a slightly smarter device. So what happens here is that if there is a frame that has to go from this host to this frame is not sent to the other connected device. only directed communication and broadcast, that is effectively broadcasted to everybody, goes out to multiple hosts, and therefore this can perform much better because the bandwidth used by these two, for example, will not affect the bandwidth between these other two hosts. Okay? So this is how switches work today. Let's talk about sniffing. Sniffing is a technique used in many attacks, and it's a way to access traffic. The basic idea is that the attacker sets his interface in promiscuous mode. That means that it asks the operating system to pass on not just the frame directed to the Ethernet card and the specific address of the device, but all the frames that are observed over the wire. It's called promiscuous mode. Of course, if there is a switched Ethernet and this attacker wants to sniff the communication of two other hosts, there are some tricks that need to be used in order to convince a switch to provide the traffic. And why is sniffing performed? But fundamentally because there are protocols that have sensitive information that is sent in the clear over the network, and you want to access that information. For example, FTP, POP, and IMAP have clear text versions that just transfer the passwords in the clear over the network. And also, by sniffing the traffic, one can access more information, like, for example, find out which hosts are visited by a certain browser or a certain user, and so this is very useful. There are a number of sniffing tools. These are tools that are used to collect traffic, and these are tools that are used by not just hackers, of course, but system administrators, whoever has to understand and debug how a network is working. There are command line tools. One of the most famous is tcpdump that allows you to collect traffic. Once you collect a dump of traffic, for example, you can use tcpflow to get the dump, so all the traffic is collected and saved to a file. tcpflow will reassemble the different streams, as we will see when we analyze TCP, we will see what this means. But you can see instead of single packets, you can see complete conversations between two hosts. And there is also tools like TCP slice to cut in different pieces, or TCP replay, which can take a recorded network traffic conversation and replay it on the network. And this tool in particular is extremely useful for testing. For example, if you're writing a program that detects an attack on the network, instead of having to run the actual attack to see if it works, you run the attack once, you record the traffic, and then you use TCP replay to play the traffic all over again to test your system. These are command line tools that you launch from the terminal. The advantage of these tools is that can be easily scripted, it can be used in a cron job, or can be automated to operate on a large scale. Sometimes, however, you would like to see something more user-friendly, and so there is a tool called Wireshark, which is kind of the state-of-the-art in network analysis, and this allows you to see the packets and to actually parse a number of protocols that are transfer over the network. And so Wireshark has a lot of very good parser that allow you to see specific field inside specific packets. It is very useful. Talking about tcpdump, so we will briefly see how it operates. It's based on libpcap, which is a platform-independent library that we will use throughout the class to build tools. So it's a very useful library to know how to operate and use. And tcpdump fundamentally allows to specify with an expression which packets are of interest to us. Of course, if you want to sniff the network on a Unix system, you need root privileges. So you need to be able to operate as an administrator. Of course, if you are operating on an existing dump of traffic, it's just a file. And in that case, you don't need root privilege. These are a series of examples of command line options. There are tons of command line options. There are a few things that you have to remember. For example, one is the -n option that tells tcpdump not to translate IP addresses into names. This is important because oftentimes students forget about this and they find that there are long delays in printing out the output of the tool, and this is because the tool is resolving names and taking time to do that. Another interesting one is the -s, the snapshot length. Make sure that you set that to either 0 or 65,536 to make sure that you always capture the entire packet from the network. Because sometimes tcpdump, if you don't specify the length of the captured packet, could capture just a portion, the one that contains interesting information and not all the data that is contained in the packet. But of course, as we say, read the fine manual. If you do man tcpdump, you'll find out all the things that you can do with these tools. As I say, with tcpdump, you can use a filter to express what you're looking for. For example, you can say, I want to see only traffic for a specific host. You can see host longboard, or you can, of course, do host 128.111.48.69. You can specify a certain port. You can identify a direction. I want traffic only when the source is host longboard, or only when the destination is port 22. And so you will see only half of a TCP connection if you're so inclined. And of course, you can also specify that you want to see only specific protocols. You can use operator to combine these qualifiers, this and the previous ones, and also you can use special keyword to specify special characteristics of the traffic. You can also access the packet data itself, so you can actually have something that specify condition inside a particular packet. For example, if you remember, if you look at the format of an IP packet, the first 4 bytes were, the first 4 bits of the first octet were the version. The second 4 bits were the header length. And you remember, you can say, if I do bit by bit and with 0xf, I will only obtain the lower 4 bits. So I will only get the header length. And so if the header length is different from 5, which means that 5 would be 20 bytes, which is the standard size on an IP header, then I can use this condition to find out all the IP datagrams that actually have options. These are just examples. For example, in the first case, you specify that you want to sniff for interface ETH0, do not resolve names and show the Ethernet addresses. Here you can see that we specify the size of the traffic, and we want to save the traffic, going to write everything that we see to a specific file. But once again, the man page is your best source of information for this. As I said before, tcpdump is based on libpcap to perform sniffing. And libpcap is very simple. You just fundamentally open an interface, okay? For example, with pcap open live, you can of course also open a file for reading or a file for writing. But fundamentally, once you compile and set a filter that specifies which traffic you're interested in, you enter a pickup loop in which you record you associate a callback so that every time a packet is returned, your function is called, and at that point, you receive a packet with this very generic structure with just a timestamp and the content of the packets, which is a chunk of memory, and then it's up to you to cast the content of the memory to extract and parse the various protocol contained. First the IP protocol, for example, then the TCP protocol inside IP, and after that any subsequent higher level application protocols that are contained. So this is how you sniff traffic. But if you remember correctly, we talked about switched environments where there are switches and not hubs. And in that case, libpcap is not enough because you're not seeing the traffic. So you have to find ways to access this traffic. And historically, there have been a number of ways. Every device has its own, if you want, idiosyncrasies. There are some switches that actually provide a special port called the span port, where you can actually connect and see all the traffic. This is provided in switches and routers so that, for example, network analysis tool or security tools can be connected and they don't have to resort to any special trick in order to access all the traffic. But if you're attacking a network, you can have other solutions. One is to perform MAC flooding. The idea behind MAC flooding is that in order for a switch to operate as a switch, they have to remember which MAC addresses are associated with each port of the switch. So suppose that they have, a limited amount of entries that they can remember because they make the assumption that there will never be more than, a few devices attached to a specific port. So if one device sends very many MAC addresses to one port, the switch might sort of overflow and decide that it cannot handle this many MAC addresses, and the only solution to the problem is to revert to a hub-like behavior and start broadcasting everything. Another possibility is to perform MAC duplicator or cloning, in which the attacker decides to send to impersonate the MAC address of one of the victim whose traffic it wants to access, and send this type of traffic to the switch, which will now record that a MAC address is actually present on 2 ports, and when a packet arrives, will duplicate it. But of course, this type of behavior depends really on how the switch is implemented, what are the security mechanisms that have been configured for the switch, and so on. A more reliable approach is ARP spoofing. In an ARP spoofing attack, the attacker fundamentally sends forged ARP reply packets to the host in the network to try to convince them that the Ethernet address associated to various IP is the address of the attacker. By doing this, the attacker can act as a black hole and receive all the traffic, and after the attacker receives all the traffic, it can decide whatever they want. They can decide to actually route them to the correct address and act as a man in the middle, can drop the traffic and cause a denial of service attack, or other sorts of shenanigans. So let's see how ARP spoofing works. If you look at this scenario, we have a host A, host B, and the attacker, host C. And they're all connected to a switched Ethernet network. That means that when host A talks to host B, host C will not see their traffic. But host C doesn't like that. It wants to be able to access the traffic. So fundamentally, host C sends a first message to host A, say, oh, by the way, ARP reply, if you want to talk to host 110, the Ethernet address is bad, like in this particular case. So the attacker is sending to host A a message to create a mapping between the host B IP address to the Ethernet address of the attacker. And as you can imagine, there will be the same type of attack that is performed on the other side, where host C sends an ARP reply to host B saying, by the way, if we want to talk to host A, 1100, the Ethernet address is bad, which once again is host C. And as a result, as you can see now, host A has in the cache that the association of host 110 is with address bad. While, after this, host B also believe that the association with the host 100 is with Ethernet address bad. So after this attack, you can easily imagine when host A wants to talk to host B, it goes in its cache and say, okay, I want to talk to host 100. I have what host A thinks is the Ethernet address of 100. So it takes an IP packet that is destined to 100, but it puts in an Ethernet frame that goes to host C. Because the switch is making this decision only on the Ethernet address. It's not looking at the IP address that is inside the frame. The only thing that matters is the Ethernet destination address. So the packet is actually sent to host C. Host C can access the information and now can send the correct Ethernet address to host B, because in this way the communication is left open and nobody really observes anything weird. Everything happens as it should. So by doing this, you can fundamentally completely control a network and the delivery process, the direct delivery process. Of course, every once in a while, legitimate ARP replies might reestablish the right mapping between IP and ARP addresses, and therefore these ARP attacking tool are continuously sending ARP replies to make sure that the right binding are performs. And there are several tools that allow you to run these attacks. Of course, you can write your own as well. This Sniff is one of these tools. Is actually a collection of tools that provides the ability to perform ARP spoofing attack, but also, of course, combine that to do DNS spoofing, because ARP spoofing can also be used for full impersonation. For example, you can obtain all the traffic that should go to a DNS server and reply with your own version of the mapping between IP address and domain. But also, this Sniff provides tool to extract information from the network, extract email, observe downloads, and so forth. Another tool that is incredibly useful is EtherCap. EtherCap is specifically tailored to perform man-in-the-middle attacks, especially ARP spoofing attacks, but also other attacks like DHS injection attack to race with a DHCP, not DHS, DHCP server. And it also provides support for the interception of Secure Shell 1 and SSL connection and sniffing password on the network. And we will see a little demo now. So let's see if I can make this work out. So here we have 3 hosts. Okay, let me log in briefly. Now, okay. Perfect. So here you can see we have 3 hosts. We have user Alice on host Wonderland. That's the Alice on Wonderland reference. And this is user Bob on host Jamaica. Okay? And if you use these 2 hosts, they're on the network. And this 3rd host is the attacker, which on the same network. So if I look at the first host and I do arp-a, as you can see, it has a number of entry in the ARP cache. In particular, it knows about host 221, 192.168.15.221, which happens to be this host. And let's see if everything is correct. If I do ifconfig at this host, if I can spell, you can see that this host is effectively at 192.168.15.221, and the hardware address is 000C29A6B233, which is exactly what is represented there. And then there are 2 entries, one for the DHCP server and one for the gateway. Those are irrelevant. Of course, if I'm on host Bob and I do arp-a, I will have the dual situation. I will have that this host knows about 192.168.15.220 at this particular hardware address, and this is our host A. So if I run ifconfig here, you can see that the hardware address on this is 0C29B30D3D, which is exactly what is represented here for IP address 220, which is the IP address of these 2 hosts. So the 2 hosts have already talked to each other. They've established their mapping and everything else. We don't like that because we want to be able to intercept their traffic. And so here we launch ettercap. And let's see if I can. Here, you can see that in this case, I'm launching ettercap, and using the textual interface, I want to do a man-in-the-middle ARP attack, and I want to have it between 220 and 221. These are my 2 target addresses. So with ettercap, what you do, you sort of describe 2 groups of hosts. In this case, these groups of hosts are just 1 host each. And you say, I want to intercept communication between any hosts between these 2 groups. In this case, only 2 hosts. So when I go here, what happens is there is ARP spoofing attack in progress. So now, when I perform arp-a, you will see that 221 is no more at the address that we have here, okay? That is B233, but 221 is now associated with 786F, which happens to be also the MAC address of 227, which is the IP address of this machine. So effectively, this machine has convinced this machine that the Ethernet address associated to the IP address of this machine is this one, okay? And of course, they did exactly the same thing on the other side. So if I do arp-a here, you will see that, once again, you have that 220 is now associated with this MAC address, which happens to be exactly the same of 227, which is this machine. So unless you would look at the ARP cache, you wouldn't notice anything different. Why? Because ettercap takes care of forwarding traffic between the 2. So for example, if I go on Jamaica, and I do netcat listen 1337, netcat is a very simple tool that allows you to create and shut down communication, socket connections, or create services between 2 hosts. So here I'm listening to port 1337, and here I do NC, and I'm going to 192.168.15.221, so host Jamaica on port 1337, and I write something, I say, for example, ciao, you can see that the string ciao has been transferred correctly. But the packet that contained this data have been sent to this host and from this host to this host. And of course, you can imagine that if I answer meow, this traffic goes to this host like it would if there was no attack, but the packets have actually been going through the attacker. And by doing this, the attacker can see the content of the conversation even though A, B, and the attacker, Alice, Bob, and the attacker are on the same switch network, and they shouldn't see each other's traffic unless they're directed that way. Now, we're going to do a different variation that gives you an idea of how powerful this attack can be. So I launch a new attack, but this time with a filter, because you can actually launch the attack and you can specify how you want to modify the traffic between the two. Because with this, we can sniff traffic, but what if we want to do something more? So in this case, I decided, for example, I start the same service, I connect, and I just told EtherCap to make some modifications. So now when, for example, user A say this demo is rather lame, you can see that on the other side they say this demo is rather lit, because actually I created a filter that would find in the communication every instance of the word lame and will transform it into lit. So this shows that using EtherCap you can actually take not only sniff the communication but also act as a man in the middle and modify however you want. Okay. Let's go back to our presentation. So we talk about EtherCap, and how powerful our ARP spoofing attack is. Of course, there are ways to prevent these ARP spoofing attacks. One thing is to not use ARP as a protocol at all and create static entries that define the association between specific IP addresses and specific hardware addresses. Of course, this becomes very difficult to handle in very large deployments, but maybe you could use it for hosts that you know are very critical, like DNS servers. Also, you can resist cache poisoning, for example, by ignoring replies that are unsolicited. ARP is a stateless protocol, and therefore it doesn't check that a reply has been sent in response to an actual request, and that's what allows ARP spoofing to work so effectively. So this is one possible way, or to create some kind of monitoring EtherCap as a module to identify suspicious ARP behavior. An ARP spoofing attack can be very noisy because you have to continuously insist on sending updates to maintain the right connection between IP addresses and Ethernet addresses. And there are tools like ARPWatch and others that allow to detect this kind of attack. Of course, if you're on the same host and you look at the specification of the network interface, you can notice that a flag called the promiscuous flag is set. That would be indication that somebody on the host is actually sniffing traffic. But of course, if you have kernel level access, you can easily create a rootkit that would prevent that flag from being displayed. You can also do other things. You can look for suspicious ARP activity. We have seen that an ARP spoofing attack is actually pretty noisy. You can also look for suspicious DNS lookups. So imagine there is a sniffer, and that sniffer has been set to resolve name for some reason. And so when it sees traffic to a specific IP address, even if that traffic is not directed to that host, it will try to resolve the host. And so one can say, hey, you never talked to that IP address. Why are you trying to resolve that name? That could be used as an indication that somebody is sniffing. Another one would be latency. So the basic idea is that since the network interface, the NIC, is in promiscuous mode, is processing all the traffic. So if I send on a network a ton of traffic that is not directed at that host, and I measure if that host has been impacted from the performance point of view by this traffic, for example, looking at response time, I can determine that there is actually sniffing activity. Other things, you can look at specific kernel behavior. For example, in certain versions of Linux, if there is an Ethernet packet which has the wrong Ethernet address but the correct IP address for that host, that packet, when the network is in promiscuous mode, will be passed up to the operating system, and therefore you could have, for example, the sniffing host respond to pings even though the ICMP packets are encapsulated in a frame that doesn't go to the hardware address of the host who's sniffing. And many of these techniques were included now 17 years ago in a tool called anti-sniff, but in general it's very difficult to detect sniffers. So one thing that you want to do, for example, is prevent people that you don't want to get in your network or on your network in the first place. One of these mechanisms is called 802.1x. It's a port-based access control. The basic idea is that every time you plug it into a network, you're giving very minimal access, and only after you have authenticated yourself using all sorts of different mechanisms, username, passwords, or whatever else you're using, only once you're verified and identified, you can actually access the network in a normal fashion. Let's talk now about IP spoofing. We saw sniffing as a building block for network attacks. Let's look at spoofing. In spoofing, fundamentally, you want to impersonate, okay, a host on a directly connected network. And this is as simple as putting the correct fake source address in your IP packet and then sending the packet exactly as it would be done normally. So for example, in this case, we have the attacker who's on host 2121 who wants to send something to 2014 pretending to be a different host. So the attacker will simply create an IP datagram that appears to come from 2076 to 2014, and then it will put it in an Ethernet frame that in this case is from this device to this device. But this host will not care, will just receive the frame, extract the IP address, and interpret that IP datagram exactly as if it would have come from this device instead. So the packet is spoofing. Why somebody would do something like that? Well, because you want to impersonate at the IP level somebody else. You might want to appear like the DNS server. You want to appear like a specific host that has some trust relationship that is based on the source of the packets. And there are actually protocols like the network file system that in the good old days utilize the IP address of our request as a way to authenticate the user. And there are many tools to do this. We will see one in specific. If you want something easy on the command line, hping is very useful. But even more useful is libnet. Libnet is a library. You can see libnet as the dual of libcap. libpcap allows you to sniff the network. Libnet allows you to create and inject packets on the network. And fundamentally, it allows you to fundamentally initialize some memory, fill in a chunk of memory with all the different content, and just send the packet on the wire. And using libnet, you can fake any aspect of the protocol. Here is a very simple example that simply creates the packet, and I'll show exactly where. Here, create a first version of the packet, initializing the packet by passing the size, then opens the link on the interface. Here, construct first the Ethernet part of the packet. With this libnet build ARP, we'll create the ARP request, the ARP reply that we use to perform an ARP spoofing attack. And then simply, we'll say, inject the packet on the network. And then close the link. And in a few lines of code, you can have a process that will just, if you compile the code and you send spoof, you will see the spoof packet being sent to the network, and you will see that the actual ARP cache has been modified. Of course, libnet is a C library that allows you to build very high performance tools like libpcap for sniffing and injecting packet. And once you master libpcap and libnet, you will be able to fundamentally create any kind of network tool for attack, for defense. It allows you to receive and manipulate traffic as you want. Sometimes you don't want to create a super high performance network tool. You just want to have something that allows you to operate at the network level in an easy fashion. And then the tool for you is scapy, which is a Python library that allows you to actually sniff and inject traffic by just using a few Python lines. And it's very handy in a number of ways. We talked about spoofing. We talked about sniffing. Let's now talk about hijacking. And in hijacking, this is almost a combination of sniffing and spoofing. And what happens is that the attacker is observing an interaction between two people and trying to inject a reply in order to, for example, race against a legitimate server. So a type of hijacking would be, once again, something that AutoCap is able to perform for you, DHCP hijacking attack, where you see a host asking for an IP address, and before the legitimate server provides the IP address to the host, it is the user that injects a reply, and in addition to the IP, provides a number of extra information, for example, the DNS server, the gateway, and so forth. And by doing this, can control the way in which the attacked host actually perceive the rest of the internet. In order to run this attack, of course, you have to observe the DHCP request, so you have to be able to sniff, and then you have to be able to inject a reply that appears to come from the legitimate DHCP server, and therefore you need to perform a spoofing attack. So hijacking can be seen as a composition in most cases of sniffing and spoofing in directly connected network. And in the next series, we will actually look at how these attacks can also extend to indirect delivery, so to communication between hosts that are not in the same subnetwork. Thank you very much.